why we're here. Sam is going to defend his thesis. It's a very nice thesis. It's a very solid thesis, a good example of a thesis. Sam was supported in his research in part through IRIS, the Interdisciplinary Research Institute for the Sciences. The director of IRIS is here, Julie. And that was a big help, I think. There's some new unpublished results in this thesis, which will be published in a NOVA book. It's a chapter in a NOVA book called Recent Advances in Cosmology. And so what we'll do is listen to Sam's presentation, and then afterwards we'll subject him to questions of any type. And, I may have some technical questions as well as some questions about the connection to middle school.
No questions during the presentation. No.
Well, maybe we should. Yeah, that should be all right. Yeah, take questions. Yeah, because that's probably the right time to ask them.
Thank you, Dr. Klein. This presentation is going to be on Fermi coordinates in the inflationary power law cosmologies. If you've read the thesis, the thesis also includes a chapter on relative velocities, which I'll speak about if I have a chance, but this is the meat of it, so I really wanted to make sure I covered this. And my name is Sam Haven. I want to thank everyone who's here, everyone who traveled to be here, but especially my advisor, Dr. Klein. He showed me what it means to be a researcher. None of this would have been possible without him. And I also want to thank IRIS for their financial support. So the three big parts of this talk: a little bit of background information, Fermi coordinates in general. If the title is Fermi coordinates, I should explain what those are. I don't think everyone in the room maybe knows. And then specifically in what are called inflationary power law cosmologies, which is where the big results are. I'm going to assume that to some degree you know what a manifold is. Maybe if it's just on an intuitive level, it is. If you don't, what everyone says, that it's an object that locally looks like Rn, that for the most part is going to be good here. And if there are notions that I need beyond that, I'll try and explain them as I go. But again, in the thesis itself, there's an entire chapter on mathematical preliminaries. Trying to make this talk, and I realized that it could take the entire hour, or an entire course called 550 to really do that justice. So I have to assume some of it. We're going to use units where the speed of light is the number 1. So you're not going to see the letter C show up, and that's because of that. And if you see a superscript and a subscript with the same index, that means we're summing over that index. And if the index is a Roman letter, the sum goes from 1 to 3. If it's a Greek letter, the sum goes from 0 to 3. I don't think there are any other ranges of summation. So cosmologies, the study of the large-scale structure of space-time, and any study of space-time requires general relativity, which expands on the ideas of special relativity. Just some more background. The metric tensor, I'm going to refer to that object a lot, and one way to think of it is it measures the degree in which the Pythagorean theorem fails on that manifold. So in standard Euclidean space, the metric is just this crazy symbol here, Kronecker delta ij. It means that, if you haven't seen that, to use full shorthand, and so what that ends up giving is this line element, which gives us this, the distance formula that you're used to. One way of writing that. So there's a certain kind of manifold that's all I really care about. It's called a Lorentzian or pseudo-Riemannian manifold, and that means the signature of the metric tensor is 3, 1. Informally, you have 4 dimensions, 3 of which are like each other, 1 which is different, as has been noted in some of my sources in there. That 1 dimension that's different is time. The 3 dimensions that are similar are the 3 spatial dimensions. Just for completeness, the Einstein field equations, which is what general relativity really is, describes the metric of the universe, of space-time. And this is how you can write it because of all the summations, or because of the indices are hiding that this is actually a lot of equations. In one, it's a system of coupled partial differential equations that relate the metric, and that you see here, and also these terms are derived from the metric. And so the metric is related to this guy here, which tells you the distribution of matter and energy in the universe. So this is saying that space-time is curved, and that curvature is dependent on where matter and energy are.
And lambda is the cosmological.
Yeah, oh yeah, actually, yeah, lambda is the cosmological constant. This guy wasn't there for a few decades because Einstein put it in to make the universe static, and then Hubble realized, Hubble's results showed the universe wasn't static, and so they took out the cosmological constant, and then we've now put it back in, and I'll mention this more later on, but there is evidence, pretty convincing evidence, that the universe isn't just expanding, but the rate at which it's expanding is going up. And so to explain that, they have this negative energy term called the cosmological constant. In cosmology, so to make those equations solvable, we assume spatial homogeneity and isotropy. That means that the distribution of matter at a given time, if you fix time, the distribution of matter should be more or less, should be even. So stuff is spread out evenly in the universe, in any direction you look, it looks the same. Now, spatial homogeneity is a simplification because, even in this room is very not homogeneous right now in terms of the distribution of matter. There's very little in like this space, but then in the space containing me, there's more. Or if you zoom out, there's a lot of matter where the sun is, not a lot of matter between the sun and Mercury. But if you zoom really, really far out, it turns out these are pretty solid assumptions. And those assumptions say that the 3 spatial dimensions then can only be one of 3 things: Euclidean 3 space, the 3 sphere, or hyperbolic 3 space. And so we don't have to write those over and over. That corresponds to this number k being 0, 1, or -1. They also give the metric, called the Robertson-Walker metric. This is the line element here. And A of t you haven't seen before, that's the scale factor. If the universe is a 3 sphere, then that corresponds to its radius. Otherwise, it's not as easy to physically describe what it is, but the scale factor gives you a good idea. The time dependence of the spatial part of the universe's size is encoded in there. Some more abbreviations. That function S sub k it depends on the curvature of the universe. Going to abbreviate more the d omega, because a lot of the time I'll just work in 2 dimensions. If we have homogeneity and isotropy, that means you don't really need to worry about what angle you're looking at because it's the same in any direction. There's a coordinate singularity that doesn't affect us, and the range of chi needs to be restricted if we're on the 3 sphere, and that makes everything messier. It still works out, but we're just going to assume we're not on the 3 sphere so that we don't have to deal with those restricting chi. Okay, so the metric's written up there so I can refer to it specifically as scale factor. So Hubble's results in the end of the 1920s convinced people that A dot was positive. The spatial part of the universe is expanding. Recently, the 2011 Nobel Prize in Physics was awarded to 2 teams whose results showed that a double dot is positive, so in accelerated expansion or inflation. A power law cosmology is one in which a of t, that function, is just t to some power alpha. And if alpha is bigger than 1, then its second derivative is positive, so it's an inflationary power law cosmology. The main result of this presentation has to do with them, so that's why I'm explaining that. But some of the results just mention these things in general.
Is there experimental evidence that this is a good model?
I do mention that there are some papers that get a good fit to k equals -1 and alpha around between 1.09 and 1.19. So yeah, and it's nice. There were the universe, like when you study the different epochs of the universe, they talk about the radiation-dominated universe where A of t is t to the 1/2, and then the matter-dominated where A of t is t to the 2/3, unless I just switch those. I got it. Okay. And so at those times, this was a good model, though alpha was less than 1 there, and so.
So it's contracted.
In those, it was still expanding.
Right.
But it was, yeah, the second derivative was negative, so it was the opposite, inflationary, at those times. And so this is still like kind of open the interpretation, but they think this lambda, whatever this cosmological constant is, like sort of has, it sort of took a while to get going. There were other forces that were winning out in the beginning, but in the end, they think it'll win out.
So this is a solution on the Einstein equation for which tense?
Well, we don't, it's, let's see, I believe it's a solution to the Friedman, let's see, equations, but not necessarily, we're using it as a model. So it doesn't, we're not worried about it solving the field equations, because, so I'm not 100%, let me.
Well, it's a little ambiguous because you can always plug the metric into the left side of the Einstein field equations, and then you produce an energy momentum tensor of some sort.
Okay.
So it's the question, what restrictions should that energy momentum tensor have? And so in these cases, you can produce an energy momentum tensor for a perfect fluid with a certain equation of state, which varies and depends on alpha.
So I'm going to use this notation a lot. M being a manifold, G being the metric tensor on it. The manifold is always space-time, and the metric tensor is the one determined by the A of t we're looking at. And V a vector in the tangent space of that manifold. So, if I use the words light-like, time-like, and space-like, it just has to do with, so the metric tensor isn't positive definite. So you can have vectors that inner product to a positive, negative, or 0 number. And so those have names in this field. We call it light-like if its inner product is 0 and it's non-zero. Time-like if it's negative, and space-like if it's positive. And paths also get these names, provided that the velocity vector to the path satisfies this at each point along the path. Null is synonymous with light-like. And, sorry to throw a bunch of definitions at you, but it's hard to not use them. And it's entirely possible. So what that would look like, more or less, is a path that did something like this. Its velocity vector at each point always stays under, above the 45-degree angle, and so it's always going to satisfy time-like condition. It's entirely possible to have a path that is neither and does some crazy stuff. Those paths aren't physically meaningful, so they don't have a name. And yeah, but that is weird. So the thing is, because it's not positive definite, the metric tensor, you can't define a metric in the topological sense, which is frustrating vocabulary. And often, I'm referring to it as the metric tensor, it's often just called the metric, but it's a different thing than the metric in the topological sense. So the metric